This problem is from the 1953 Polish Math Olympiad finals. Feel free to give it a shot and keep watching to see the solution. Okay. Okay, so with Olympiad problems, there's usually more than one way to solve it. There's usually more than one solution, so I'll show what I did. But if you have another way of solving it, feel free to share it in the comments because I want to encourage discussion on these videos. Okay, but here's what I did. So it's tangent alpha plus tangent beta plus tangent gamma. And it makes sense to ask what trigonometric identities do we know that involve addition as well as tangent? So there's tangent alpha plus beta is equal to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta. But this is with 3 angles. So maybe we can look for something similar, maybe tangent alpha plus beta plus gamma. What would this be equal to? Can we use this to help us? Well, yes, we can. We can group alpha and beta together and then plug this in here and plug this in here. So that's what I'll do. So tangent alpha plus beta plus tangent gamma over 1 minus tangent alpha plus beta times tangent gamma. Okay, and we know how to find this. It's right here. So we're just going to change these to this. Okay, so it's going to be equal to tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta plus tangent gamma over 1 minus tangent alpha plus tangent beta over 1 minus tangent alpha times tangent beta times, put a parenthesis here, times tangent gamma. Okay, so we plugged everything in, but now we need to simplify this complex fraction. So how do we do that? Well, you'll notice that there's a fraction in the numerator and the denominator, but they have the same denominator. So if we multiply the top and the bottom by that denominator, then we can get rid of the fractions that are in the numerator and the denominator. So what is this equal to? So if I multiply this with this, well, that gets rid of the denominator, and we're just left with this. Okay, and then plus this times this. Oops, okay, here we go. Yeah, I'm gonna keep, let's see, yeah, just keep them alphabetical. All right, what does this simplify as? Well, 1 times this is just this. Okay, and then minus this times this. So it's just going to be this times this. Let's see. Oh, yeah, we'll just do this. Tangent alpha plus tangent beta times tangent gamma. Okay. And then we can get rid of the parentheses here. But you'll notice that the numerator looks very similar to the problem. So that's a good sign. And it means to me that it's worth it to explore this path a little bit more, to see if it can help us find the solution. But yeah, usually if you start to see stuff matching, then it's a good sign. Okay. Yeah, I'll just copy it, but get rid of the parentheses there. Okay, so tangent alpha plus beta plus gamma is equal to this. Now, if this holds, what can we say about the numerator? It's going to be 0. So that means tangent alpha plus beta plus gamma is going to be equal to 0. As long as the denominator is not equal to 0. Okay. So tangent alpha plus beta plus gamma is going to be equal to 0. So that means, well, when is tangent of an angle equal to 0? It's when what's inside the parentheses is equal to some integer multiple of pi. Oops. But this is when the denominator is not equal to 0. So tangent alpha times tangent beta plus tangent beta times tangent gamma plus tangent gamma times tangent alpha is not equal to 1. But what if it is? Well, we need to address that case separately. So I'm going to get another sheet of paper. Okay, so, yeah, write it down like this. Tangent alpha plus tangent beta plus tangent gamma is equal to tangent alpha times tangent beta times tangent gamma. And then also the denominator is equal to 0. So, the denominator is equal to 0, so this is going to be equal to 1. Okay, so tangent alpha times tangent beta plus tangent beta times tangent gamma plus tangent gamma times tangent alpha is equal to 1. Okay, so how do we address this case? Well, there is quite a lot of symmetry here, so what are some strategies to exploit symmetry? Creating a polynomial and applying Vieta's relations is one. Um, yeah, let's go ahead and try that. I don't know if it's going to work, but let's say R1, so the root 1. Yeah, our first root is going to be tangent alpha. Second root is going to be tangent beta. And our third root, let's just draw this here, is going to be tangent gamma. And we're going to create a monic polynomial. So I'm going to say t cubed minus r1 plus r2 plus r3. Yeah, basically I'm creating a cubic with these as the roots. And I'm using Vietta's formulas to create it. Okay. And then it's minus R1, R2, R3. Okay. Now, from this system, what do we know? We know that R1 plus R2 plus R3 is going to be R1 times R2 times R3. And this is going to be equal to 1. So we can actually factor this. Yeah. I'm going to change this to R1, R2, R3 to match with this. And then I'm going to change this to 1 to match with the coefficient in front of t cubed. Okay. Okay, and then plus t, and then minus r1, r2, r3. Okay, so we can factor this, and what's it gonna be? Let's see here. So we can factor out t squared, and then it's going to be times t minus r1 times r2 times r3 plus 1 times t minus r1 times r2 times r3. Okay, and then we can factor this out. Okay, so how many real roots does this have? Just one? But R1, R2, R3 are the roots of this. And R1, R2, R3 are all real numbers. So we've got a contradiction. This polynomial has these as roots. It's supposed to have 3 real roots, but because of this, it only has 1 real root. Okay, so we have a contradiction, and so that means there's no solution to this system, which means this is the answer, but we need to clean up our proof a little bit. This is not what I would turn in, so I'll get another sheet of paper. Okay. So how are we going to write the proof? We're going to divide it into 2 cases based off of if this is equal to 1 or not. Alright. So, okay. Case 1. Suppose tangent alpha times tangent beta plus tangent beta times tangent gamma plus tangent gamma times tangent alpha is not equal to 1. Then we can use what we found out on this sheet. So how should we write it? Okay. Then, let's see. Tangent alpha plus beta plus gamma is equal to tangent alpha. Yeah, so I'm just copying this expression now. Tangent alpha plus tangent beta plus tangent gamma minus tangent alpha times tangent beta times tangent gamma over 1 minus tangent, I gotta write a little smaller here, tangent alpha times tangent beta minus tangent beta times tangent gamma, and then minus tangent gamma times tangent alpha. And this is going to be equal to what? Well, it's going to be equal to 0 because this is equal to this, and this is the same thing as this. So this minus this is 0. So let's see. Yeah, I'm just going to write that it's equal to 0 here. Since tangent alpha plus tangent beta plus tangent gamma is equal to tangent alpha times tangent beta times tangent gamma. Okay. Now what? So, what can we say about this? Tangent plus 0. Let's see here. So it's going to be okay. Well, I wrote that this is equal to 0 here. I guess we can just cross it out. Okay. So alpha plus beta plus gamma is equal to k times pi. Yeah, because this has to be an integer multiple of pi. Okay. Now, okay, I'll box this. We also have the other case. Suppose tangent alpha times tangent beta plus tangent beta times tangent gamma plus tangent gamma times tangent alpha is equal to 1. Then what? Then there are no solutions to that system. Yeah, so how do we write that down? maybe we can reuse this sheet of paper. I'll just kind of transcribe it here. Suppose that it's equal to 1, then the system has no solution. Okay, so it's going to be this, and then this. Okay. Here, I'll write this one first. Okay, and here I'll write. I should have written like I'll write claim here, and then we'll have to prove it. But yeah, we proved it by constructing that cubic. Okay. Let R1 equal tangent alpha, R2 equal tangent beta, R3 equal tangent gamma. Then, by Vieta's formulas, the following cubic has R1, R2, R3 as its roots. Okay, so here it is. T cubed minus R1 plus R2 plus R3 times T squared plus R1 times R2 plus R2 R3 plus R3 R1 times T minus R1 R2 R3. Okay. And let's get another sheet of paper. Okay. Now, let's go back over here. So we factored since R1 plus R2 plus R3 is equal to the product. All right, let's write that down. Since R1 plus R2 plus R3 is equal to R1, R2, R3, and R1 times R2 plus R2 times R3 plus R3 times R1 is equal to 1. We can rewrite, I'll just say P of T there. We can write, okay, here, let's just do this. we can rewrite PT. And then it's just, we copy this stuff here. Yeah, we'll just, so we changed it to this. Okay. This, and then we factored. But we have a contradiction here. Well, how should we write it out? Oh, okay. This cubic polynomial has two complex roots and just one real root. Has only one real root. However, its roots are tangent alpha, tangent beta, and tangent gamma, which are three real roots. Contradiction. I'll just put like, wait, should we put a white square or black square here? Let me know in the comments. Oh wait, so there are no solutions to this. Oh wait, we said that, we said the claim there, so, okay, so we'll draw a line here and say that, that they have to add up to some integer multiple of pi. Dang it, we celebrated too early. So, alpha plus beta plus gamma equals k pi. K is an integer multiple of pi. Must hold, or should I say is the answer. Let's go back to the problem. Must be satisfied. Yeah, let's just rephrase their problem. Must be I might have to cross out the white square here because we celebrated too early. Dang it. What a shame. Must be satisfied if if tangent alpha plus tangent beta plus tangent gamma is equal to tangent alpha times tangent beta times tangent gamma. Okay. Also, I'm kind of new to this, so let me know how I did. If this is if I should be putting a white square or black square here. And uh, and yeah, this is how I solved it. Okay, so yeah, this is the first page, and then this is the second page. Okay.